Everyone to the seminar today. Today we're very happy to have Tony Gherghetta from the University of Minnesota. Tony is originally from Australia and also used to be in Melbourne for some time, but now he's back in the US at the University of Minnesota. He's very well known for his work on extra dimensions, and today he will be talking about new 5D perspectives on the QCD Axion. So please, Tony.
Okay, well, thank you very much for the introduction, and thanks also for the opportunity to talk about this work. This is recent work and looking at the QCD Axion. So let me then just begin with, actually now, how do I didn't check how to move forward now.
Can you just use the keys? Basically,
yeah, I'm using the
down.
keys.
Or you can put the navigator then.
Yeah, where was the navigator? Yeah,
yeah,
that's what that was for, actually. Now I remember. Okay, so I'm going to have to keep that. Yeah, sorry about that. So yeah, so let me start then with just the strong CP problem. So the strong CP problem is well-known problem of the standard model, and it's got to do with the fact that you can allow a CP odd term in the QCD Lagrangian, where this theta parameter here comes from two sources. There's a piece coming from QCD, just the QCD vacuum, and there's also a piece coming from a phase in the quark masses. And this linear combination is what's basis independent, and this is what can give rise to physical effects. And in particular, the most famous effect of this theta bar is this neutron electric dipole moment. And you can compute the neutron electric dipole moment in the standard model, and it has this value times theta bar. And in fact, this contribution from the chiral Lagrangian in QCD was actually computed by Rod Cruther, the late Rod Cruther from Adelaide. That was one of his famous works. He computed this. So if you look at the experimental upper bound on the neutron electric dipole moment, this is the experimental bound, 10 to the minus 26. And therefore, you see then that theta bar has to be 10 to the minus 10. And so the strong CP problem is basically the question of why is theta bar so small in the standard model. And so because the solution has been around for a long time, a lot of thought has gone into solving it. And the simplest way to solve it would be to assume, and this is what was, this was plausible in the early days of QCD, that the up quark is massless. If the up quark is massless, then this phase theta is no longer physical, and you can rotate it away because you basically now have a chiral symmetry. Alternatively, you can imagine that the CP, because it violates CP, that CP is an exact symmetry, and it's only spontaneously broken in the vacuum. And so therefore, you can then, because you're starting from zero, right, an exact symmetry, then any violation of theta bar would be generated at higher order, higher loops, and that could explain why the theta bar is so small. And this is still a possibility, although most of the models that try to implement spontaneous CP violation, they are quite baroque and quite complicated, lots of moving parts. And so the third solution here, which is what I'm going to concentrate on in this talk, is the Peccei-Quinn mechanism and the axion. And this is a famous solution from the late 70s, early 80s, where you imagine that you augment the standard model with a global symmetry, a U1, which is now the Peccei-Quinn symmetry. And this symmetry is spontaneously broken at some high scale, which I refer to as FA. And when you spontaneously break a global symmetry, you produce an axion. And this axion can actually have a potential. QCD can generate a potential for the axion, and it turns out that at the minimum of the potential, you can precisely cancel this theta bar. And that's a very nice mechanism. It's a dynamical mechanism that and it's irrespective of the source of this theta bar. Remember that the theta bar had these two sources, so it doesn't care about the source. Furthermore, this symmetry needs to be anomalous, and if it's anomalous, then the axion can get a mass, and then that's also then consistent with experiment. So what are the features of the axion solution? Well, this is the kinetic term. This is the axion Lagrangian. Here's the kinetic term. The axion couples to the gluon field strength, G and G tilde, and this is the anomalous term that's generated. But it's a dimension 5 term, which means this coupling is suppressed by this parameter Fa. Then there are also couplings to photons, and then there can also be couplings to the current, axial current, which is where the fermions, standard model fermions, can appear in there. Now, the axion mass, as I said, it gets a mass purely from QCD, and basically it comes from this this vacuum energy density here from G tilde, which is referred to as the topological susceptibility. But basically, this T has the dimensions of lambda QCD. Lambda QCD is the only dimensionful parameter in QCD. So to generate a mass for the axion, it's going to be proportional to lambda QCD. And then because it couples like 1 over Fa, you see the 1 over Fa squared that also appears in the mass term. Now, there also is a light quark contribution as well. That's the origin of this 1/8. So this is a fairly robust prediction from QCD that you get this axion mass. However, there's also another feature of the axion solution that's got to do with the global symmetry. And that's because we introduced this global Peccei-Quinn symmetry, this U1 symmetry, but it turns out that quantum gravity always violates global symmetries. And the violation is proportional to 1 over m Planck to some power. So the m Planck here is telling you that it's coming from quantum gravity. And so this is just a generic result of quantum gravity, that it just doesn't preserve global symmetries. And so if the axion is coming from, say, this scalar field, then what can happen is that you can destroy the axion solution. And so what you have to do is any term that's allowed by the symmetry needs to be suppressed to very high order. And you can imagine that this n starts at like 5 or 6, but if you actually put in 5 or 6, you find that the axion solution is destroyed. And in fact, you have to go all the way out to n equals greater than 10, so phi to the 10th. So that's a large suppression that's needed, and you have to find a way to engineer that. Now, there is a caveat here that if you imagine that these violations of gravity come from what are so-called gravitational instantons, then these coefficients Cn, they could be exponentially suppressed. But it's not clear if this really can always work. And so I'm just going to assume that there is a problem here where this Cn is of order 1 and you need this n bigger than 10. So that's the axion quality feature, or the axion quality problem associated with the axion solution. The other thing is that you can ask is that, well, where does this dimension 5 coupling come from, right? If you go back here, there's this new mass scale that appears in the standard model. Well, where does it come from? And again, back in the early 80s, this question was addressed, and the origin appears is that you introduce new fermions, which are charged under the Peccei-Quinn. You also introduce a new scalar, which is also charged under the Peccei-Quinn. And then this scalar, you can think of it like a Higgs field. This scalar will have a potential, and if the mass squared of the quadratic term is negative, then you can actually generate a VEV. And here I've written it here, right? And you can identify that VEV with this scale FA. And indeed, you can take the complex scalar you can put in the VEV, which is FA over root 2. And again, it's just like the Higgs. You have a VEV here, V over root 2. And here's the radial mode. And then the axion just sits in the angular part of this exponential. And so phi here is a complex scalar. There are actually 2 degrees of freedom, rho and A. And then the fermions, these fermions that you added in the theory, you can decouple them because these fermions psi couple to this scalar phi. So when phi gets a VEV Fa, these fermions then get a mass of order Fa times some Yukawa coupling. And when you integrate out these fermions, so these are the fermions here in this triangle. This is the axion. These are gluons, external. You actually generate this dimension 5 term. And so that's a very nice way. So you see you're starting from a renormalizable Lagrangian with a renormalizable potential with the Yukawa couplings, and you're generating this dimension 5 axion gluon coupling. So that's where the dimension 5 axion coupling comes from, but you still have to explain what's the origin of this mass scale. Notice that this Fa here, it depends on MPQ, and MPQ is just put into the scalar potential. And it's a bit like the Higgs, right? We know that the Higgs gets a VEV of 246, but where does the 246 come from? It's also a similar question. Now, there also is another version where you don't introduce new colored fermions. You actually introduce, you extend the Higgs sector, and you have an extended Higgs doublet, a 2 Higgs doublet model, plus a complex scalar. And that can also do the job as well. And that's referred to as the DFSZ model, which appeared around the same time. But those are the 2 kind of UV completions of the dimension 5 coupling. And so right now, here's the, I mean, again, this is quite standard. The limits on the QCD Axion searches, it's been looked for a very long time. And the axion decay constant, that's another name for this Fa, is roughly between 10 to the 9 and 10 to the 12 GeV. And because this Fa is it's a pretty high scale, right, compared to the electroweak scale, then the couplings of the axion are suppressed, and this is why the axion is basically called the invisible axion. Furthermore, because the axion gets its mass from QCD, once you fix Fa, right, there's no other free parameter here. Once you fix Fa, and the Fa is kind of fixed from experiment, once you fix Fa, then the axion mass is fixed. And this is the mass range for the so-called QCD axion. Now again here, let me stress I'm referring to the QCD axion, which means that I'm trying to solve the strong CP problem and also potentially be a dark matter candidate. So that's what I'm referring to here. Now, you can add generic axion-like particles, but that's not what I'm referring to here. I'm literally want to solve the strong CP problem. So therefore, the questions then that I'm interested in at the moment would be, what is the origin of the axion potential? Where does it come from? And where does the spontaneous breaking scale, how does it arise? Furthermore, how do you solve the axion quality problem? And then also the other question is, can the axion mass be different? So is the axion mass really just, the QCD axion mass, is it really just tied to the QCD scale, or can you modify QCD to make it different? And so what I'm going to do to address these questions is the 5th dimension. I'm going to use the 5th dimension to address these questions, because some of these problems are actually very similar to how the 5th dimension was used to try and explain electroweak symmetry breaking and the Higgs mass and the composite Higgs. And so what we'll see is that that framework of using the 5th dimension can also be applied to the QCD axion. So let me then jump in now, jump into the into how to go about solving the axion quality problem. And so this was work done with Peter in Melbourne, and also my student Ming in Minnesota. So what we're doing here is, again, we're going to use the fifth dimension, and you might think that the fifth dimension is a bit it's a bit rich to use it. I mean, you're going for an overkill, you're kind of adding in all this structure, but we'll see that there's a reason why we do that, and it's got to do with the ADS CFT. I'll get to that shortly. But right now, we can just think of this as basically a Randall-Sundrum setup where we've got the fifth dimension. So I'm going to refer to Z as the fifth dimension, and X are the four space-time coordinates. So here is a brain, a 3 brain with a UV cutoff, and then here is an IR brain. And as you move into the bulk of the fifth dimension, which is compactified here, the cutoff decreases as you move into the bulk. And so immediately you can see that if the axion is associated with the infrared brain, then you can immediately explain the Peccei-Quinn scale, just like Randall and Sundrum were explaining the Higgs mass scale as due to a warp factor. So that gives you that pretty straightforward. And so the only thing that we have to do then is just modify the usual Randall-Sundrum setup with this Peccei-Quinn symmetry. So we're going to put this Peccei-Quinn, see, Randall-Sundrum had the standard model in the bulk, but here I'm just going to put for now the Peccei-Quinn symmetry in the bulk. It's going to be preserved in the bulk, and it's also going to be preserved on the IR boundary. And the only violation of the Peccei-Quinn symmetry is going to be from the UV brain. And the reason I'm doing that is so that I can mimic the effects from quantum gravity. So allowing this violation on the UV boundary will mimic these effects from quantum gravity. So here's the Lagrangian. There's a bulk vector field, bulk scalar field, and the axion. Here's the axion. The axion is going to be part of this bulk scalar. So you can now go ahead and solve this model and look for the axion.
Can I ask clarifying question quickly?
Yeah.
So the whole standard model is confined to the brain. The instantons and so on are the usual 4-dimensional. Is that correct?
That's correct. They're all confined here right now.
Okay.
That's right. Yeah. And then depends on how much time I have. I'm gonna put the I'm gonna talk about the instantons and the 5D model at the end if I have time. But right now, yeah, I'm not doing that. That's right. And so now it's just a question of solving this model. And I don't want to get into all the details there, even though I've written out the action, etc. But it's just a standard procedure that you solve this action with boundary conditions. And here are the boundary conditions. The boundary conditions are just chosen so that you have a spontaneous breaking of the Peccei-Quinn symmetry on the IR boundary, and you have an explicit violation of the Peccei-Quinn symmetry on the UV boundary. And that's basically it. And you can solve for the scalar profile, and it has this form where delta here is a free parameter. K is the scale of this warped background. It's just think of it as like related to M Planck. And lambda and sigma just parameterize the explicit breaking and the spontaneous breaking. And that's it. And I don't need to go into any further details here unless people have questions. And so at this point, so that's the solution. And you say, okay, well, you've solved this this 5D action with the bulk VEV. Why did you do that? Well, the reason is as follows, and that's because this 5D theory, which I've indicated here on the left-hand side, the 5D theory is actually dual to a 4-dimensional gauge theory. And that's the interesting thing. So indeed, I put a Peccei-Quinn symmetry in the bulk. I chose this delta parameter. By the way, this delta parameter, it was just related to the bulk mass. So just think of a delta as a bulk mass parameter. I had the warp factor in the bulk, and I had these two parameters, sigma and lambda. But you can map all these parameters to a 4D gauge theory, where you do have a global symmetry, where you turn on an operator, a condensate of the Peccei-Quinn symmetry of dimension delta. And then in this four-dimensional gauge theory, you also generate an infrared scale, and this infrared scale would be related to the decay constant. And then you can also spontaneously break the Peccei-Quinn symmetry or explicitly break it. And so that's why one performs these calculations in this warped background. But at the end of the day, what we really have in mind is we have in mind that there's a 4D gauge theory. And so that means that if I end up solving the problem in 5D, I've then got to tell you, well, how did you do it in 4D? What's the solution in 4D? Because maybe I don't like the 5D setup. And that's and I'll give you that answer shortly. So this is then the bulk equations of motion. Again, yeah, I don't really want to get into too much detail here. You solve the bulk equations of motion. The only thing here I'm pointing out is that they're nonlinear and coupled. And so when you do a Kaluza-Klein expansion, you have to actually expand the axion field and the fifth component of the vector field. They both have the same 4D expansion. And so the axion contains a bit of the scalar field and a bit of V5 or VZ. These are the boundary conditions that you get. And then you can first of all just check that everything worked as expected. And so the first thing to check is that when you remember, this lambda parameter was proportional to the explicit breaking. So if you turn that off, what you should find, if you've set up the boundary conditions correctly, is you should find a massless axion, because you're just spontaneously breaking the global symmetry. So you should find a massless axion in the spectrum. And indeed, that's what you find. These are the profiles of the axion. The zero here is the zero mode, the massless axion, and you get some expressions for the axion, and these are just their profiles as a function of the fifth dimension. And indeed, you can identify this global, if you do have a massless axion, then the axion should have a shift symmetry. And indeed, you can identify it from the 5D gauge invariance. All right, so that's consistent. And so then the next thing to do is to say, well, let me now turn on the explicit breaking. So this is turning on the explicit breaking on the UV boundary. And if you do that, you're mimicking these quantum gravity violations of the Peccei-Quinn symmetry. And so you now turn on the UV potential, and indeed you see you generate a potential for the axion, that you generate a cosine potential. And if you expand out the cosine, you see now that you generate a quadratic term for the axion, which is a mass term. So that's what you expect. If you violate the symmetry, then the axion will get a mass. And then you can also look at what happens to the profiles of the axion in the 5D bulk. And interestingly, what you find is that the profile of the axion, so this was the profile of the axion, the dashed line, you find that the profile gets suppressed at the UV boundary if you take this free parameter delta and take it very large. I mean, bigger than 1. So if you make it 5 or 10, you see this suppression in the profile at the UV boundary. And at the moment, as I said, delta is just a free parameter of the 5D theory. And so I can choose this parameter to be as anything I like. But in the 4D theory, this will have a meaning and it will have a consequence. But right now, what you can see is because the profile is suppressed on the UV boundary, that means that the axion is not going to be sensitive to any violation on the UV boundary, because you have this huge suppression, which is coming from the fact that you can increase the delta. And so that's going to be the key to how I'm going to solve the axion quality problem. So in the 5D model now, I can compute the axion mass, And so here it is. This is just, again, just taking the 5D theory, compute the axion mass, and let me plot the axion mass as a function of delta. And you can see that as delta increases, and these two plots are the same, roughly, one's a log scale, one isn't. And this was in the paper with Peter. So as you increase delta, you can see that the axion mass just decreases quite quickly. And this is what we want, because this contribution to the axion mass is coming from quantum gravity, and you don't want those contributions to be big. Otherwise, you'll destroy the solution to the strong CP problem. So you've got to suppress the quantum gravity contributions to the axion mass. And that's what I'm showing you here, that if you take this parameter delta and make it very large, then indeed this mass is suppressed. But you can understand it because the profile was getting suppressed from the UV boundary. And so the axion, which lives in the bulk, is not sensitive to the violation on the UV boundary. So the other thing to do here is that there is a mass scale here. This is the infrared brain scale. So that mass scale, we'd like to relate that mass scale to the decay constant, and that you can do. And so that's what I'm doing here. So this is just, again, a summary of what I have. I have the violation restricted to the UV boundary. I have my standard model fermions in the bulk, and I can put the color, this is QCD, I can put it in the bulk or I can leave it on the boundary. Those are the two options, and I can generate an axion gluon coupling. If I generate the axion gluon coupling, then I can relate the infrared scale to the decay constant. And that's this relation here. It's off to the side here, but it's a very important relation. By using this so-called Chern-Simons term, which is the term that's allowed by the 5D theory, you can then relate the infrared scale. This is the mass scale here, Z infrared to the -1. You can identify it as the decay constant. And sorry, here I've called it capital FA now instead of little fa. And so then I can go back and rewrite my axion mass squared, and now I can write it in terms of fa squared. And then here is the suppression that you see, fa divided by lambda uv. Lambda uv, think of it as m Planck. And so there's a suppression, but notice that you get a suppression provided that delta is bigger than, is sizable, right? It's much bigger than 4. And that's the values that I was using. I was using 5 or 10, right? And then you get a suppression in this quantum gravity contribution to the axion mass. So that's the answer. That's the answer that you get from the 5D model. You see how the gravitational violation of the Peccei-Quinn symmetry gets suppressed. And it gets suppressed by taking this parameter capital delta to be of order 10. So we can actually do a bit more quantitative. We can get a lower bound on this delta. So let me now come back to the axion potential. Here's the axion potential. The first term is just the usual QCD contribution. And notice that the axion here is a dynamical field. Its minimum, notice that its minimum would cancel the theta bar, because the minimum of the cosine would be when A cancels the theta bar, and that gives you the solution to the strong CP problem. However, if you have another contribution to the axion mass or another explicit violation of the Peccei-Quinn symmetry, you'll generate another cosine potential, but the phase that comes with the other cosine potential doesn't necessarily align with the contribution that you get from the quark masses and the QCD vacuum. And so that's the problem. And so you've got to suppress this coefficient so that you don't destabilize the minimum. and this is the condition on this UV, on this gravitational violation of the mass. It has to be 10 to the minus 10 times smaller than the QCD contribution squared. And because the UV contribution depends on delta, then this leads to a lower bound on this delta. And indeed, if you put in the value of FA, that's between 10 to the 9 and 10 to the 12, then the lower limit on this delta needs to be 10. So if you want to have the axion, if you want to identify the decay constant from this extra dimension model to be within 10 to the 9 and 10 to the 11 GeV, then this delta, the minimum of the delta has to be, the smallest the delta can be is 10. And so at this point, you might say, okay, that's the parameter delta in your 5D theory. It has to be bigger than 10. And it looks a little bit bizarre from the 5D theory. And so the question then is, does this have a 4D interpretation? What am I really doing here? And the answer is, well, what I'm doing here is the following, is that I'm solving the Axion quality problem, because what I've done with this 5D model is I've set up the Peccei-Quinn symmetry to be an accidental symmetry of the 4D Lagrangian. And so this is very reminiscent of baryon and lepton number in the standard model. Notice that baryon and lepton number in the standard model, they are only violated at dimension 6. And that's just an accident in the standard model. It's just got to do with the standard model gauge structure and the Lorentz invariance. It's just, and the first indication of violation of lepton and baryon number is at a dimension 6 term. So what I've done here for the Peccei-Quinn is I've set up an accidental global Peccei-Quinn symmetry for a 4D model, which has a composite axion. And so I'm literally mimicking what we have for baryon and lepton number. And that's why this delta, you see, this delta is actually the dimension of the operator that violates the Peccei-Quinn, it's the dimension of the operator of the Peccei-Quinn condensate that violates the Peccei-Quinn. And indeed, it has to be, the dimension of the operator has to be of order 10. And in fact, this capital delta here is related to the dimension of operators in the CFT dictionary. And so that's what I had back here. You see that this delta was literally the dimension of this operator. And I'm telling you that from the extra dimension, this delta has to be smaller, has to be bigger than 10. And that's agreeing with what we expect just from the 4D, Lagrangian. In fact, I can even go back to, sorry for going back here. Oh, but now I'm, notice that when I added the explicit violation, this n had to be greater than or equal to 10, but now the model that I have, this n is the delta, and it has the same value, and that's why there's no surprise at why delta had to be greater than or equal to 10. And so that's basically how the Axion quality problem is solved. It's solved with this accidental Peccei-Quinn symmetry. Now, it turns out that people have actually made 4-dimensional models with an accidental symmetry, and it has the features that we find in the 5D theory. But let me not go into that detail right now. So instead, let me then just continue with this particular model, because now that we have a model for where the Axion quality problem is solved, you can actually then continue further with the framework to generate, for instance, Axion-fermion couplings, and that's what I'm doing here now. So I'm still using the setup where I have a violation of the Peccei-Quinn symmetry on the UV boundary, but now I'm adding the fermions in the bulk. And the reason why I'm adding the fermions in the bulk is because I also want to solve the fermion flavor problem. These Randall-Sundrum type models, they're also been heavily used to solve fermion flavor. So you can combine an Axion quality problem with fermion flavor to generate also the Yukawa couplings. And then again, this is also in the paper with Peter and Ming, but then also Quentin and Emilian Dudas. So I just want to be brief here because I don't want to go into any detail, but the upshot is that this particular model is going to also explain the fermion Yukawa couplings, and then we will also predict the Axion-fermion couplings. So the fermion Yukawa couplings, that's a well-known story. If you can create sufficient small overlap between the fermion profiles in the bulk, then you can have small Yukawa couplings. So let me not say any more here. And the only difference here is that I'm putting these fermion overlaps in this model, which solves the Axion quality problem. Okay, so this is just these are just some equations here, just to show you how you generate the Axion-fermion couplings. Let me not go into the detail here, but let me just say, however, that the Axion-fermion couplings, they're generated between an overlap of the axion that lives in the bulk and the fermions that live in the bulk. So when you integrate over the fifth dimension, you'll generate this Axion-fermion coupling. So let me just go to the result here. So here is the Axion profile. It has a constant piece, and then it has a Z-dependent part, which varies in the bulk. And if you perform the overlap integral between the axion and the fermion profile, which also is Z-dependent, then you'll generate these Axion-fermion couplings. And the notation that people use is over here in the box here. People define the Axion-fermion coupling as some dimensionless parameter, C, subscript V or A, depending on vector or axial, divided by the decay constant. And so this particular ratio is written as an effective mass scale, which is this capital F, V, comma A. And that's what I've shown here. I've shown the effective scale of the Axion-fermion coupling as a function of a free parameter that exists in the 5D model. So this free parameter, it's related to the fermion mass spectrum. It's an order 1 parameter, and it just varies, just around the origin order 1. And you can see that depending on the flavor of the fermions, you can generate off-diagonal couplings to the axion. And here are the quark off-diagonal couplings in the up quark, and here's the down quark, and here are also the leptons. And you see that these scales are roughly 10 to the 12, 10 to the 13, 10 to the 14. Now, what I should say here is that these particular couplings are generated for the solution that explains the fermion Yukawa coupling. So these aren't just random Axion-fermion couplings. These Axion-fermion couplings are being generated in a model where you also explain the flavor structure. And so these are the values, and then this is people put their experimental limits on all these couplings, and the best experimental limit right now is the 1, 2 in the down sector. So that's down strange. And the lower limit on that coupling is 6.8 10 to the 11 GeV, and that's coming from kaon decays into axion. And that's what I'm showing here, right? I'm showing this 1, 2 coupling as a function of this free parameter in the extra dimension. And the shaded region down here, that's the limit, the lower bound. And you can see that it's already ruling out some parameters in the 5D model. And the future sensitivity that you can find in this paper, which I believe is, it's 2 10 to the 12, that they believe they can go up to 2 10 to the 12 in the not too distant future. And you can see that's this dash line, and you can rule out more of the parameter space. So this is a function of sigma naught, which is a parameter in the 5D model. But if you want to see it as a function of delta, it gets very interesting, actually, because, well, it's interesting in the sense that right now, the values of delta that are ruled out and wouldn't work for the quality problem, right? Here's delta equals 6, but the future sensitivity will start to probe the values of delta, which will solve the Axion quality problem. So anyway, so that's all I want to say on this first part of the talk. So maybe I should pause here and let people, if they have any questions, because I can also check the time. Okay, so I think I have another, do I have another 15 minutes left?
Yeah, that's fine. That's fine.
Yeah, okay.
Can I ask you one question?
Yeah.
Just here, since so in the usual QCD Axion models, the couplings of the axion to the fermions are proportional to the mass. Do you still have that here for the the diagonal couplings?
Yeah, you do. Yeah, it will be proportional. That's right. You can relate it, because I don't have those expressions here, but you can relate these couplings. I don't have an expression. Well, it's just this C parameter here, this Cij. You can relate this to the fermion masses. Yeah, you can do that.
Yeah,
but
thanks.
But we didn't have. Yeah, but I don't have those expressions for you.
Mm-hmm. Yeah, no problem.
Yeah. All right. So then, in the remaining time, I'm just going to switch gears now. Oh, Axion, did you have a question?
I had a more general question, which is extremely interesting. You know, so maybe we can discuss this later. But if you have a quick answer for this, because so what you're really talking about, I mean, this suppression of quantum gravity kind of effects. Well, the usual thing, you know, the discussion is kind of is related with the Hawking evaporation, where the global charge is lost completely, and the thermality of this evaporation. So what you're really saying is, in that language, that you may supply whatever 5-dimensional black holes you have there, or 4-dimensional counterparts, with some type of here. You know, through this gauging. Yep. Is that what is happening there qualitatively?
Yeah, exactly. Yeah, that's right. Yeah, that's right. From the 5D perspective, you see, you've got a local symmetry in the bulk. That's right. Yeah.
Okay, it's interesting. Yeah, thanks.
Okay, so let me just finish up in the last now probably 12 minutes. But I just want to give you the idea of the second. The second question I wanted to address, which is also related. This was work done with Valya, Koza, Alex Pomeroy, and Yuri Sherman, and this was just looking at the axion mass and seeing if you can actually modify the axion mass, so the QCD axion mass. So let me recap here. So the QCD axion mass, as I said, it just comes from the vacuum energy density of this topological susceptibility, and it's also related to instantons via this dilute gas approximation. And so this T, this topological susceptibility, notice that it depends. It's exponentially dependent on the value of the QCD coupling at the size of the instanton. So the instantons are conformal. You can have them any size. So you can just think of this as just some energy scale, but it depends on the size of the instanton. And because QCD is asymptotically free, if you go into the UV, so take very small size instantons, you know that the QCD coupling is very small in the UV. And so this denominator is small, which means this exponent is very large and negative. And so small instantons do not contribute to this integral. Instead, the integral is going to be dominated when the coupling alpha S, QCD coupling, is large. And of course, it's large in the infrared at the QCD scale, which is roughly 300 MeV. And so indeed, this instanton integral here is dominated by lambda QCD, which is the scale in the infrared where the QCD coupling is large. And another way to say it is that the usual contribution to the topological susceptibility is coming from the large instantons, which is where the QCD coupling is large. Now, there's also a further suppression due to fermions, but it's important, but let me not dwell on this. There's a further suppression to this integrand, which is proportional to the fermion mass. So let me just leave it at that. But this is the idea here, is that the coupling is and the size of the instanton is what controls how big this exponential is. And so, but notice that once this is proportional to lambda QCD, the Axion mass is fixed. The only freedom you had was in the decay constant. So the question then is, how would you go about changing the Axion mass? Well, the only way to do it would be that you would have to change the QCD coupling in the UV. So this now is saying that you've got to add some new physics into the UV such that the coupling doesn't go to zero. Alpha S doesn't go to zero in the UV, but maybe it rises again and becomes of order 1. And now you will get a contribution coming from, because you're at very high scales in the UV, that corresponds to small instantons, and you might get another contribution coming from the small instantons. There's also, again, you can also enhance the Axion mass by using Yukawa couplings as opposed to the actual fermion mass. But let me not go into that because I won't have enough time. But the bottom line is that if you allow these small instantons and this coupling to change in the UV, then you can see then you get a new contribution to the Axion mass. And so again, I'm going to use the fifth dimension to make the QCD Axion heavy, because I'm going to let the fifth dimension is one way for which the coupling, the QCD coupling, can actually grow again in the UV. So let me not worry about how you set up the calculation. I don't have time for that. Let me just jump to the kind of the bottom line here. So here's the cartoon of what's happening. So I'm plotting this exponential that I was referring to, this e to the minus s, where s is 2 pi over alpha. It's written here. That's the first piece, and I'm plotting it as a function of the size of the instanton. And so normally this contribution e to the minus f just falls off exponentially, because what's happening is as you go into the UV, this is as I'm moving to the right here, the energy scale is increasing, or the instanton size is decreasing. So the usual 4D story, QCD story, is that this exponential contribution just dies off exponentially. But if you imagine that in the UV at some scale, intermediate scale, there's an extra dimension, then you can alter the gauge coupling, the alpha S, and then this exponential can actually rise again. The effect of this exponential can actually rise, and you can get a new contribution. And so you can take the model and you can calculate this contribution. And what you find is you find that there is this power law term with a negative sign. And so as rho is the instanton size, as you take rho to 0, you can actually kill off the large. You see, this factor here is becoming large and positive because alpha S is going to 0, right? QCD is asymptotically free. But you can halt that behavior because you can subtract off this large contribution, negative, that's coming from this extra 5D, from the 5D scale. And so that's the origin of how you can change the axion mass. And let's see here, what else? This is just a technical point about higher dimension terms that I don't really have time for. And now let me just get you to the result. So again, this is now the axion mass compared to the value that you get in QCD. And so I've put in all the factors. There are a bunch of prefactors which I didn't really explain to you, but just have to assume there's a bunch of prefactors. But then here is the two effects that I was referring to. You can see that's the QCD effect, and then you've got this extra effect coming from the 5D enhancement. And so this 5D enhancement can help you make the exponential become dominant again in the UV. Now, of course, what happens is that the theory is becoming strongly coupled, and there is a question of is your Lagrangian, are higher dimension terms, is your expansion, is it valid? And that's a valid question, and we can address that with these higher dimension terms, which I don't have time to explain right now, but I can definitely go into more details about that. But then here are the results. So the blue and the green curves just show you the enhancement depending, the blue and the green just tell you whether you have higher dimension terms or not. And you can see that as the extra dimension, depending on the scale of where the extra dimension appears, the enhancement, so you want an enhancement, you want to be bigger than 1. You can see that you can get an enhancement provided that this epsilon parameter, this epsilon is a measure of the perturbativity of the 5D theory. So epsilon equals 1 would be the red line here, and epsilon being 0.3 or 0.2 is kind of a semi-perturbative, you're getting close to the perturbative limit. But in any case, you can see that these small instantons are giving a new contribution to the axion mass, and they can dominate for extra dimensions which are bigger than 100 TeV. So so you don't have to put extra dimensions at 100 TeV. You could put them up at the gut scale or even the string scale. So that's the effect of this extra dimension. Let me see here. But by the way, this is not a new idea. We certainly weren't the first to have this idea. In fact, the idea actually appeared pretty shortly after in the early 80s, where people had the idea that if you could make QCD strong again in the UV, then you could turn on these small instanton effects and get a new contribution to the axion mass. And then more recently, people have started to look at this again, enlarging the color. And then there's also you can also get a large axion mass with a mirror QCD. But the bottom line of this story is that the axion mass now it is sensitive to the UV completion. So we don't have to assume that that the axion mass, that the axion gets its mass just from QCD in the infrared. We could have a sensitivity to the UV, and what this does is it opens up parameter space. So when you have a heavy axion which solves the strong CP problem, now you've got more motivation to look for the QCD axion. So this is not a plot from, this is just a plot from this one of the papers, one of these papers here from the enlarging QCD color. So it's a pretty busy plot. I don't really want to explain everything here because it's not my paper, but the black line here is the QCD axion. And normally we stay on that line if you want to solve the strong CP problem. But if you can now modify the QCD mass, right, then you can go off this line, and you can now explore other regions of parameter space for which you solve the strong CP problem. You see, this plot is for the usual plot for ALPS, right? ALPS live off the, right? They don't solve the strong CP problem. You either solve the dark matter or not. And so people have explored just generically just random axion masses, but the story here is that you could move off the QCD axion line and still solve the strong CP problem. At least that's the hope. And I just want to point out these solid lines. These are the values from this paper for which they solve the strong CP problem. They have two benchmark models, and you can see that it doesn't live on the QCD axion line. Sorry, I don't have a plot for the paper we wrote, but I have a student now looking at it, and eventually we'll have a plot as well. Incidentally, there was also a recent paper by Quintano, which also used this UV contribution to actually improve the naturalness of the axion dark matter. Normally, if you have decay constants of 10 to the 15, 10 to the 16, the misalignment angle has to be quite small. But if you allow for small UV instantons, then you can actually get decay constants around the gut scale to work for misalignment angles of order 1. And so that's an interesting paper as well, which relies on this UV small instanton effect. All right, my time is up. Sorry for going over. So here's the conclusion. The axion quality problem, I showed you how it can be solved in a 5D warp dimension. But again, don't get hung up on the 5D warp dimension. What the solution is really capturing, it's capturing a dynamical or composite axion with an accidental symmetry. And we see this story in the standard model. Once you have that framework, then you can go and look at a model which can explain the fermion mass hierarchy and then predict these off-diagonal Axion-fermion couplings. And then in the second part, or in the latter half of my talk, I also showed you how it may be possible that 5D small instantons can enhance the axion mass. And this is interesting because that means we should be exploring the full parameter range, because it could be that any axion mass could be solve the strong CP problem and then be a sensitive probe of UV physics. So that's it, and thanks very much.
Yeah. Thank you very much, Tony, for a very interesting talk. Now we have time for questions. Who wants to go first?
May I have a question first?
Yeah.
Tony, yeah. The thing is that I have to run for the faculty meeting soon.
Yeah,
so
sure. Yeah, no
I
problem.
have a lot of questions actually, but one of the things which I also thought that I still want to understand, for example, this from not from the model building perspective, but from the conceptual things, how this model or potentially could work. So if you have a 5-dimension without any compactification, for example, right, as a starting point, then I think there is no instantons in that model, in a sense that the instantons are unstable. The topology is trivial, right? And so in that case, you don't have a CP problem as well, because you don't have a connection between this vacua, right?
So indeed, but in order to get finite action, you have to have a finite. You have to have the extra dimension needs to be compact. And so your question is related to this here, actually.
Yeah, if I take a R to
infinity, you see. If you take r to infinity, then it's e to the minus s, and you'll get 0. Yeah, exactly. There's no finite action solution in 5D, so that's right. So this solution, this 5D solution, can only exist for a finite size. It's not going to.
Yeah, but what I'm saying is that in principle, if you have a very large volume or size, of you should have a suppression between the transition between the topologically inequivalent minima.
Yeah, but,
well,
but
right?
that's this.
So that's another kind of.
See here.
Yeah.
No, but you'll see it if you take r to infinity. You'll get that suppression. Indeed. Yeah. No, that's true.
Okay. All right. Now it's all interesting, and the thing with the black holes is also presumably interesting, which could have thought that way as well.
Yeah. No, that's why I really was I was disappointed when I couldn't when I couldn't come because I wanted to discuss all this stuff with you and with the group. No, it was a very disappointing year. But okay, but I'm sure it will happen. We'll get to discuss it further. Yeah, because I'm still interested in these questions.
Yeah, I think we'll have to continue discussion. Thank you, Tony. Yeah.
So there are more raised hands. I see Bruce and I see Mike Toba. So Bruce has to run off also soon. So maybe.
Hi, Bruce. How's it going?
Good to see you. Going well. It is very good to see you. And thank you for the talk. Extremely instructive. Could you just duck to page 13 for a moment? There's something I'm not understanding. So you pointed out the suppression here on at the UV brain, and I get that. But just looking at this, the suppression seems to be more extreme for the lower value of delta rather than the higher, and all of your discussion has been in terms of what happens.
But you see, yeah, but no, that's right. But you see it here though, that in fact it's the higher value of delta actually has a larger suppression. This is kind of a blow up in this region.
Right. Okay. Sorry, I've missed the inset. I see.
Yeah. No. It's because. It's because I didn't emphasize it because I was falling behind and I didn't emphasize it. No, I should have emphasized it, and that's what's going on. So it still is consistent. You see how the
so that's a very peculiar shape then, because it has.
That's right. Yeah.
So there's a.
That's right. Yeah.
Right. So that's an extremely non-trivial shape.
Yeah, it is, because what's happening is that as you increase delta, it's actually becoming flatter and flatter, and then it just drops down.
Okay.
Yeah. And we checked that. Yeah, I mean,
that's very non-trivial, and
exactly.
I think I understand the use of these dual theories and their utility better on the basis of this talk as well. So thank you.
Oh, thanks, Bruce. Yeah, thanks.
All right, so I need to drop out, but thank you very much.
No worries. Yeah, I hope to catch up with you in person at some point. See ya.
We have another question from Mike Toba.
Yeah, thanks. That was a nice talk for an experimentalist. I could follow, I think. I was in your last figure where you were showing the coupling, you were showing the photon coupling.
This one here?
Yeah, so yeah, this one. So I noticed with those benchmarks, they actually make it harder to detect the QCD Axion with experiments, and which is unfortunate. I don't know what your model will predict, but but in your model, you're only looking at QCD, you're not looking at interactions with, say, spins and photons. Can you put spins and photons into your model? And
no, we can. Yeah, we can. It's just that we haven't done that yet. No, that's
for someone like me, that would be the most interesting thing to do.
Exactly. Yeah, no. Yeah, thanks for the question. Yeah, because what I want to do is I want to do with my student, we want to look at something more phenomenological. So forget the theory. So now one can look at it more in a more phenomenological setting and just see how much of this parameter space you can actually solve the strong CP problem.
Yes. Do you expect that you might get modifications to the way you couple to photons and spins?
Yeah, I believe so. Yeah. No, I believe, yeah. That's got to do with because you can play around with this 1 over FA. So that's definitely something that we want to look at. And yeah, because we know that this is a very active experimental area. As you can see with all these lines, and so we definitely want to provide more information. The other interesting thing is also to put on here where it actually solves the dark matter, because you see, I think if you hone in on where you solve the strong CP problem and the dark matter problem, that would be definitely very interesting experimentally, right? You should then concentrate on those regions. But you see, I don't know where those regions are on this plot, and that's what I want.
There's been some work by I think Raymond Coe, this thing called cogenesis, where the axions produced in the early universe, but they're quite different to QCD axions. I mean, maybe there's a place where they're both the same or something. I don't know.
Actually, yeah, one of the authors, he's a postdoc here in Minnesota, actually.
Oh yeah. So that's a nice paper, because it says axions might be easier to detect.
Exactly, yeah, because they have the ALP cogenesis, which is above it's above the QCD axion line.
Yeah.
So
our experiment's about to start tomorrow, organ experiment, and it's about to look in a certain regime.
Right.
It'll be starting.
We just it would be good to have something that kind of has these more generalized QCD axions and with the dark matter, and because if you solve two problems, and if you have a region of parameter space where you can solve two problems, then that's very interesting. See, right now there's only a small region here where on this black line where you actually, if you solve the strong CP and the dark matter, I believe you're roughly here.
Where this smash theory predicts a certain range. We're starting off at 15 gigahertz and going up, where no one sort of looked. It's where Mad Max is meant to look, but where. I see. Yeah.
But if we can expand that out to go and say, like, go over in this direction or come down here, or that might not be so good. But if we can expand it out, we can motivate other regions. Of course, I mean, this doesn't. Of course, people should still look for axions in this region. I mean, I'm not saying not to do that, but I guess we were just trying to, hopefully, to provide more motivation.
I want to look where theorists tell me to look.
Oh, okay. Yeah. Well, isn't it also, you're not supposed to trust theorists as well?
Well, there's so much space, you might as well look where someone tells you. It's probably more probable.
No. Actually, what's interesting on this plot here is that they've got the PQ quality lines, which you normally don't see. And you see, if you have dimension 5 turns, the QCD axion needs to be above this line, you see? So if you believe in the PQ quality problem, all this space just wouldn't be consistent with quantum gravity. So, I mean, you see, but anyway, you just take that with a grain of salt, because, you know, it doesn't mean that no one can come up with a model which puts you down here, but that's precisely, there are models. I mean, I talked about the model today, but there are other models that put you down here. But that shows you how severe this PQ quality problem is.
Another interesting thing is you were talking about quantum gravity. You have to do something to quantum gravity to cause this that makes this suppression, but we don't really have a theory of quantum gravity. We don't know what quantum gravity is. So we're also doing precision experiments to look for quantum gravity. With your calculations, is there other experiments that would be consistent with your suppression factors, or delta 10 or something? That's just a out there question, you know, because we're looking
definitely exploring quantum gravity or Planck scale couplings. No, that's definitely well motivated, because you see, that's okay. Let me say it this way. That's more motivated than what I'm telling you here, even though I probably shouldn't tell you that, but no, but it's true, because we know that gravity exists, and we know that quantum mechanics exists. So those effects have to be here.
So I mean, there's experiments with optomechanics. We do some in our lab with. Could any of those have any input to these theories as well? I don't know.
I think so. No, I think so because what you can then be sensitive to is because what you're doing is you're sensitive to very weak forces, right?
Yeah.
And so you could probably be sensitive to these other forces. At the end of the day, right, this is just another force. It's actually stronger than gravity, and you could be sensitive to that as well. No, indeed, yeah. But my point is that, you see, this whole QCD axion, it could be that that's not the way nature chose to solve the strong CP problem, and that there are no axions. That's what I was getting at.
Yeah, I realized that. Yeah.
But I would say, well, I don't know. I mean, I'm a theorist. I'm biased, but I would say
I'm an
that
experimentalist and unbiased.
I would say that the axion is really simple and elegant, but you never know, right? Nature might choose these spontaneous CP violation models, which are completely different. So I don't know. Yeah. But definitely, if you have something that's sensitive to like gravitational forces, then you're going to be sensitive to anything that's larger than gravity, by all means. Yeah.
Okay, thanks.
But by the way, Mike, I mean, you're at UWA, right?
Yes, that's right.
Yeah, because my parents I'm from Perth, and my parents live in Perth, right? So
you should come out. Yeah.
Yeah, no, I'll have to come out, and actually, yeah, I'll have to come out and find you next time I'm in Perth. But